All right, welcome to your first lecture for Physics 2426. So as we get going, we're going to start off looking at the electric charges. We're going to go through electric charges, electrostatics, then we're going to look a little bit at circuits, move into magnetism, electromagnetism, come back to circuits once we've learned a little bit more, and end with optics. So everything up to including optics, which is lenses and mirrors, everything has to do with deriving and arriving at an understanding of how electricity and magnetism are two sides of the same coin. The equations that define this relationship are called Maxwell's equations, and there are 4 of them. We will actually encounter the first of Maxwell's equations in our first module. So everything we're trying to do is come up with that unified theory. And then at the end, optics, which is based on light, which is an electromagnetic wave, is based on the electromagnetism as well. So this is going to be very different from what you have seen in mechanics. So mechanics dealt a lot with your forces, pushes, and pulls, but most of your forces were contact forces. The exception was gravity, and we're going to revisit gravity a little bit today. Electromagnetism is more based on fields and non-contact forces, and we'll have some very different approaches. Now, that doesn't mean we're going to completely forget about all the mechanics that we have learned. You will have to use it. We'll see some of it here today. The other thing you're going to find is there is a lot more calculus involved in many of the concepts that we see, and a lot more three-dimensional aspects of kind of physics. So what we're starting with is going to look a lot more like mechanics, but as we start getting through, you're going to see how we start deviating from that. And depending on what experiences you had with your Physics 1 course, it may look very, very different to what you've seen before. So my biggest suggestion as we start here with lecture 1 is that as soon as you don't understand something, get help. Because this class goes so fast, you don't have time to go, oh, well, I'll probably catch it later, because you won't in most cases. It may click later a little bit better, but if you are lost on the fundamental concepts in these lectures, you need to get help because they come up again and again and again. So let's dive into it. All right, so starting with electric charge. So this is hopefully something that you have heard about before. So it is an intrinsic property of matter itself, kind of like mass. So the charges that we have are positive or negative. Positives are often associated with protons, negatives are associated with electrons. That's at a subatomic level, but when you look at the quantum scale, it's actually the quarks that are what are responsible for the charges. And when you get lower than quarks, you start looking at muons and things, and it gets all beyond almost all of our heads. So we're going to look just kind of at that subatomic level. This is going to be based on our understanding of physics in the early 1900s. We'll pull in some more stuff from more modern physics, but most of it's going to be based kind of on kind of our basic understanding of charge that you've been looking at since chemistry and so forth. So we tend to use the symbol Q for charge, a lowercase or a capital. It kind of changes. A lot of times we use a lowercase for a variable and a capital for a constant for when that charge is fixed. The unit of charge is the coulomb, which is a capital C. But actually, an individual proton or electron has a very, very tiny amount of coulombs worth of charge. So even if you have a whole bunch of charge, it's still not going to be 1 coulomb. It's going to be some times 10 to the negative something. So a lot of times you will see microcoulombs, you'll see nanocoulombs, and even picocoulombs as you go through and do calculations. But anytime you're using our formulas, you need to be in that SI unit of coulombs. So you might have to do some unit conversions with your metric scale. If it's been a while since you've done some of those unit conversions, especially on this small scale, I do suggest you check out a video tutorial on that, as I'm going to assume that you know the metric scale going here on out. Now, the two kinds of charge positive and negatives. Like charges are going to repel, so positive repels positive, negative repels negative, and then unlike charges, so opposites attract. Okay, not groundbreaking here. There's also a law of conservation of charge. Because charge is fundamental, way down to the quantum level, the total amount of charge that we have is going to be constant. It can get transferred between objects, but the total amount is saved. There's nothing on the formula sheet that specifically says this. It's just one of those fundamental truths that we may sometimes have to use when solving problems. So our charges are quantized. Our electron went away. That was kind of fun. Not sure why it did that. But our electrons have a negative charge, protons with a positive, but they're quantized. So all charge comes in multiples of this value E, which is 1.6 times 10 to the negative 19th coulombs. So that is the charge of one proton or one electron. Now, neutrons aren't really uncharged, but they have a neutral charge because they have equal amounts of positive and negative charges inside of them. Actually, if you were to kind of peek inside of a neutron and kind of look at the quarks and stuff, a neutron is really basically a proton with a negative charge kind of stuck onto it. And the mass of the electron is so much smaller than the mass of a proton that the mass of the neutron and the proton are nearly identical. So, and actually thinking about chemistry and nuclear physics and so forth, beta decay occurs when an electron from the nucleus gets ejected. Well, how could that happen? That's because a neutron gets converted into a proton, and that's how the atomic number changes during beta decay. Kind of side note for those chemistry people in the room. So, with that fundamental charge, Millikan came up with this experiment where he took an atomizer, which basically misted oil, kind of like perfume. And when that happened, it would actually create negatively charged oil droplets. So what he had was he had two plates, a positively charged plate and a negatively charged plate. And he had this mist of oil droplets that would kind of fall through a hole in the positive plate. And so they would start to fall. And what he found was that gravity would pull those droplets down, and the negatively charged droplets would be repelled by the negative plate and attracted to the positive plate, so you get this upward electric force. And what he did is he adjusted basically the power supply that the plates were connected to until those forces were equal. And looking through kind of a hole in his device, he was able to see when those oil droplets became stopped in the air. Some would keep following, the bigger droplets would keep following, and then he would kind of do some calculations and relate that. So by looking at all of the different droplets and everything that he did there, he figured out that all of his droplets all had a charge that was a multiple of this 1.6 times 10 to the negative 19th coulombs. So that's how Millikan kind of came up with this idea of the fundamental charge of electrons. And later on, we were able to figure out that the protons and electrons had to have that exact same charge. So when you look at a helium atom, your helium atom in the nucleus has those positive charges and the negative charges on the outside. And I think this electron ran away because only the electrons can be freed from that atom. Basically, the strong nuclear force holds together that nucleus, and those positives, those protons are stuck there. Whereas the electrons are further out, and they are much freer to leave the atom and get ionized away or get attracted back towards. So when we talk about a charged object, therefore, a charged object usually has more than one extra electron or one extra proton. So we can use this equation to describe this quantization. So Q would then be the charge of an object, N would be the total number of excess protons or electrons, and E would be that elementary charge. And of course, the negative would be for extra electrons, the positive would be for extra protons. So as you go through, that equation's on the formula sheet, but it's important that it's excess. So if I was to say have, some sort of object here with different protons, electrons, and so forth, and I was to lose some electrons because they left, when I went through and did this calculation, I would use only the excess charges. So if I were to look at my atom, this guy's gone already. This guy was gone already. And so then, okay, those are paired, so I can ignore those. These are paired, so I can ignore those. Those are paired, so I can ignore those. Those are paired, so I can ignore those. Actually, right now, we only have one excess proton, so my N would be 1. So it's not the total number of protons or the total number of electrons, it's whatever's excess when you account for the fact that a positive and negative will cancel each other out. So when we're talking about materials, we will talk about conductors and insulators, which is something you might also have heard about in chemistry and have just basic experience with. So our conductors are going to be materials that have an atomic structure that allows for the free movement of electrons. These are generally going to be materials that have weaker atomic cores or larger atoms where the outer electrons are very, very far away from the proton core. And in most cases, these are going to be our metallic elements. So copper, aluminum, silver are good conductors. But it's important to realize there's no such thing as a perfect conductor because our materials always have protons and electrons in them. Holding on to those electrons is going to occur naturally for the atoms. That's what holds the atomic structure together. So there's always going to be a little bit of insulation with all of our materials. But if we have a good conductor, then what's going to happen is if I was to say take a charge and kind of try and place it onto this conductor, all of those electrons are going to try and repel each other, and they're going to repel each other until they're about equally distributed around the surface of the sphere. In 3 dimensions. Okay, so this is kind of a 2-dimensional image, but you got to picture that those are 360 degrees around, equally distributed. Now, it won't be perfect because there's no such thing as perfect, but it'll be pretty close to it. On the other hand, with insulators are materials that are able to more strongly hold on to their electrons. So they're going to have stronger atomic proton cores that are going to be either more protons or there's going to be less shielding between the electrons and the protons in the center. So those materials are going to be things like glass, rubber, and wood, tend to be non-metals. There's, once again, no such thing as a perfect insulator. So all insulators will allow charge to flow through over time. But for most part, pretty good for that. So we have like a conducting wire made out of like copper for our house. It's wrapped in something like plastic so that when you grab the wire, you're holding onto the insulating part and you're not getting shocked by the charges moving through the copper wire inside. Now this is kind of a cool image. So this is a lab scan showing charge distribution of a sphere. It's just a surface distribution. And what you can see is the green represents neutral charge and blue is negative charge, red would be positive charge. So we know that this is going to be an insulator because we have clusters of positive and negative charges. If this was a conductor, you wouldn't have clusters. You would end up with this kind of green shade kind of everywhere because the positive and negatives will all end up spreading around. Well, actually, the negatives spread around to cancel out the positives. One thing we have to be very careful of is that those positive charges do not move. It's always the negative charges that move and redistribute themselves because those positive charges are trapped inside the structure of the atom. Now, there are 3 methods of an object becoming charged. We can charge by friction, we can charge by conduction, and we can charge by induction. So starting with friction, this is probably the one you're most familiar with, because if you've ever pulled clothes out of the dryer and felt that kind of static tingle, or had to take a sock off of a sweater, or been walking in your house in slippers and reach for a door on a dry day and get shocked, that's because charging by friction occurred. So this occurs when two neutral objects have different electron affinities. Electron affinity is a chemistry term that describes how good an atom is at attracting electrons to itself. The triboelectric series is kind of a way to describe that, and they were able to come up with this before we actually really understood what was actually going on the atomic side, just by experimentation. So the objects that tend to be more negatively charged are at the bottom of this list, and those that become more positively charged at the top. And remember, they're positively charged because they have a tendency to lose electrons, so they're not very good at holding on to them. And these have a greater tendency to gain electrons. So they're going to have those stronger attractions with their proton cores. So the way you would use like a series like this is you would take two materials and rub them. So let's say I take PVC, vinyl chloride, and I rub a piece of silk on that vinyl chloride. So because the vinyl chloride is lower on the list, it's going to have a more tendency to gain electrons. So it's going to end up with a net negative charge. So the electrons are going to get stolen from the silk, and the silk is going to end up with a net positive charge. Not because it's gained protons, but because it has lost electrons. Now, on the other hand, if you take that same piece of silk and neutralize it, basically by touching it and making sure that the charge is kind of spread around, you take that silk and you then rub it on a glass rod. If you take the silk on a glass rod, that silk, which became positively charged when rubbed with the PVC rod, when rubbed with the glass rod instead, that has the higher electron affinity, so it's going to become negatively charged, and the glass rod is going to become positively charged. The further apart the objects are on the triboelectric series, the better the transfer is going to be between the charges. Now, there's a little bit to do with like the material, so like a fabric is going to be better at transferring charge. If I rub the piece of glass directly on the piece of PVC, even though they're really far apart, there's probably not going to be a lot of transfer, just because the fibers from like silk or wool or something like that is going to kind of have a big difference. So if you take, say, like a rubber balloon, or whatever the balloons are actually made out of, kind of like in a wool sweater, you're going to kind of get that. So if you've ever charged up a balloon so you could stick it on a wall, you're taking advantage of this charging by friction. They do get charged equally but oppositely. So let's take a look at a simulation. So looking at the simulation here, you can see that all of my objects, the wall, the balloon, and the sweater, are all starting out neutrally charged. They have equal protons and electrons. So if I take the balloon and I move it over here on the sweater, I can see that that balloon has gained negative charges and the sweater has lost them. So the protons in the sweater haven't moved. They've stayed in place. I've just removed the electrons. So now those can be attracted to each other. On the other hand, if I reset that and I take two balloons and I try and rub those together, because they would be at the same position on the triboelectric series, there's not really going to be any net transfer of electrons, so they don't get charged. Similarly, if I bring one of these balloons over, let's reset the balloons back to 1, over here to the wall, nothing's really happening as I rub here with the wall. Apparently whatever these materials are pretty similar, so we're not going to have a big change. There might be some small change, but not. So we have that. Now, charging by conduction requires the physical contact between conductors. So this does not work with insulators. Charging by conduction. So kind of like with the friction, the electrons are going to flow. But in this case, they flow towards the less negative object. Or when we get into electric fields and electric potential, there's a little more detail to it. So this is kind of a very elementary kind of description of charging by conduction. But if we look here, we have this highly positively charged rod. When they draw these diagrams, they don't always show all charges. It's just a representation. So this object probably has electrons. It might have a few electrons. Well, let's pick a different color. It might have a few electrons mixed in here, but the idea is that it has a lot more protons than electrons, so it's positively charged. Whereas we have this neutral metal sphere over here that, if we count, should have equal numbers of positives and negatives. Now, if you were to touch these two conductors together, basically what happens is these electrons are all here kind of crowded in together, and there's not as many electrons over here. There's a lot more protons. So some of these electrons are going to get attracted and get added on over here to the rod, and they're going to kind of spread themselves out equally. So what ends up happening is they're not really showing everything, but you do see there are less positive charges because they're basically canceling out the paired positives and electrons, showing just the excess charges. And same thing over here, they're showing that basically I've lost some of those electrons, and so now we have excess positive charges on both objects. So your rod is less positively charged, but your sphere is now more positively charged. So both objects are going to change charge, but they do have to end with the exact same sign of charge. They will both end positive, they will both end negative, or it's even possible for them to both end neutral. If they were identical objects, so if they were the exact same size spheres, they would end up with the exact same charge. But if I have like a big sphere and a small sphere, they'll both end up positive or both end up negative, but they won't end up with the exact same charge. Later on, this unit or next unit, we'll be able to actually figure out how much charge each of them has, but not yet. So when we bring objects together, when we start looking at the neutral objects, they don't always have to gain or lose charges. It's possible just for the charges to just kind of move around in reaction to the presence of charges. This process can cause polarization. Now, you might have heard the word polarized before. If we take a look like at a water molecule, you got your oxygens and your hydrogens. They're in a tetrahedral format. And if you were to draw a line kind of across that tetrahedral structure, what ends up happening is those electron pairs kind of on the one side create a partial negative charge on the oxygens, leaving the hydrogens as partial positive, because those electrons are kind of built into that bond right there. And that's why the water is polarized. It's a dipole. It's because its atomic structure, molecular structure, means that it is already polarized. That symbol, if you haven't seen it before, is the Greek letter lowercase delta. It means kind of partial. So the same thing can kind of happen in any object temporarily. So let's go back to our simulation. And if I take a look at my balloon and I charge up my balloon on the sweater, if I bring this now charged balloon close to the wall, if you look what's happening to the wall right there, the negative charges in my balloon are repelling the negative charges in the wall, kind of exposing that proton kind of core in the wall. So if I were then to kind of do that same type of analysis that I did with the water and kind of look at my screenshot right here, if I were to draw a line kind of right here through the middle, I can see that over here there are a lot more negative charges. So that side of the wall is partially negative, and then this side of the wall here is partially positive. So I have kind of not charged my wall. It's still going to be neutral. I haven't lost any charges, but it's kind of temporarily partially charged on one side or the other. So that when I let go of this balloon, well, it's more attracted to the sweat over there, but I can then have that balloon be attracted to that wall. And you can do this on your own if it's a nice dry day. Take a sweater, take a balloon, or if you don't have a balloon, take a styrofoam plate, or something like that. You can charge it up on your hair, charge it up on your sweater, and you may be able to get it to stick to the wall depending on kind of the paint and stuff that's on your wall and kind of how dry it is. It works a lot better in the dry rather than in the humidity. So that's polarization. Now it's going to be important because our next type of charging is charging by induction. Now this is a much more involved process than either the other two methods of charging. So what we're going to picture is that we have a negatively charged rod and we have this metal sphere. It's on an insulating base, so it's basically isolated. And I'm going to picture that this neutral sphere is made out of positive and negative charges. And the negative charges and positive charges, we assume, be kind of equally distributed, but there's no net charge. So what happens is if I bring that negative charge closer, then that is going to repel my negative charges to the other side. Now remember, the protons don't actually move because they're locked into that atomic structure, but my negative charges are going to kind of move over to the side. So that if I was to kind of redraw what's going on, I'm going to end up with kind of my negative charges kind of over here off to the side. So it's now polarized because if I were to draw that line down the center, I can see that the left side is definitely more positively charged and the right side is more negatively charged. At this instant, if I were to remove the rod, the charges would rearrange and reseparate. So I actually haven't charged anything. It's still neutral. Just the presence of this rod has caused a shift. So if I want to actually charge by induction, I need to find a way to get rid of some of these electrons. So we do that by the process of grounding. We connect a conducting wire from the negative side of that, down to the ground. And what that allows us to do is if we picture the ground, it is neutrally charged. It's also very large. And so these electrons here are all like really crowded on this small sphere, and they see this neutrally charged, more spread out space, and they're like, hey, there's a lot less potential there, and they actually go from high potential, kind of like high energy, and they flow down here. And they get added, not necessarily all of them, let's just move 2 of them over there, down to the ground. Now, once again, if I was to remove the rod while that grounding wire is connected, those electrons would get attracted back up to that more positive sphere. But while this rod is in place, I have now lost 2 of my negative charges. And then if I remove the grounding wire, I have that single negative charge there. And so now I can see that not only was it polarized, but I now have a net positive charge. And then if I were to remove the conducting rod, that electron would kind of move itself kind of towards the center of all of those kind of protons. And then you can see that the outside of my sphere would now kind of, if I were to look at the sphere from the outside, it would appear positively charged. So I have a net positively charged sphere. Now it is possible to charge this the other way. So if I wanted to actually charge it up and become positive, or well, I guess that was positive, to become negative, I would just switch out my rod. So if I were to bring a positive rod in there, and I'm starting off with my charges, in this case, my negatives would be attracted. So my negatives would end up moving that way. And then if I attach the grounding wire, when I have my neutral thing here, basically what happens is what the ground sees is the ground here, the electrons here at the ground see this positively charged area right there. And they're like, oh yeah, non-anthropomorphized electrons, of course, are going to get attracted up. And so we are actually going to gain electrons while that rod is in place. I then disconnect the grounding wire, notice that my ground is now also charged. It's actually positively charged in this case. And then I remove the rod, and then my electrons will redistribute themselves. So I've got my original electrons, and I've got my new electrons, and now I have a net negatively charged rod. This is something you can actually do. It's a little tricky to accomplish, because actually having fully isolated conductors is tricky. A tool that scientists often use to kind of study electric charge is called an electroscope. The basic, most important part of electroscope is, of course, it is isolated, but you have a conductor here, some conducting knob right up here at the top, that is connected by a conductor inside of insulators to often two gold pieces of foil. That's one of the better ways to do it. They need to be foil lightweight so that you get more motion out of them, but there's a lot of different ways to do this. And then basically what you can do is kind of analyze the behavior of that electroscope. So if I picture that my electroscope starts off, neutral, so we're going to have some charges on the different parts, then those leaves are basically going to hang straight down. So if there's my little connecting rod, little thing, the leaves are going to hang straight down. But if the leaves become charged, then they're going to repel each other, because they're all touching the same thing, so they all have to be the same charge, but they will repel and open. So kind of going through some of the processes that I did before, if I picture that I brought like a negative rod nearby, what would happen is that those negatives would be repelled. So maybe some of these negatives up top would get forced down the leaves. So now the leaves are negatively charged, so they will repel and they will separate further. If I were to bring the rod even closer, it would get even more negative and the leaves would spread apart further. Or if I found a rod that had more charges that would have a stronger force, then the leaves would separate. So it can give me kind of a qualitative way to analyze the relative strengths and signs of charge. Now, this just tells me one charge or the other, but I could also do this kind of with charging up. So I could actually charge my electroscope. I could do it by conduction, or I could do it by induction. So if I wanted to do that by induction, same idea. Let's say I take that negative rod here. So I'm going to move those negative charges down. So I've got negative charges down here. Well, and then what I could do is, and a lot of times we're doing this ourselves, so we could actually be the ground. And if you were to touch the grounding wire here, then your positive knob up here would attract negatives. And so then we could actually charge this guy up negative. And we charged it up negative, and then I removed the grounding wire and I removed the insulator. Those negatives would spread themselves out along the rod, and my leaves with the rod moved away would still be negatively charged, so they will start out separated and repelled. Then, for example, if I brought let's do a positive rod this time. Draw a positive rod. That's actually going to pull my electrons back up. So some of these electrons might go back up, and my leaves that are separated will now be less negative, and so that will actually cause the leaves to collapse in and fall. So you will see electroscopes in like conceptual questions, where they ask you to kind of analyze what would happen if you brought this positive rod near, or this negative rod, or you conducted it, charged it up, all sorts of different things. Now, talking a little bit more about the distribution of charge in conductors. So far, we looked mostly at a sphere. When you look at a sphere, we assume that the charges are distributed equally around the outside. Now, this is kind of silly because my protons can't be sitting on the outside of a sphere. in reality, kind of like I showed you before, the protons would, of course, be in the material of the sphere. But if I have a net positive charge, my electrons are going to be, now this is looking inside. This is like a slice. So if I'm looking at a slice, my electrons would be hanging out more towards the center because there'd be a higher density of protons. So that if you were to look at the outer part, so if I took away the inner part and I looked at the outer part, that outer part does have positive charges. Okay, so that's part of it to realize. Some of these diagrams very much misrepresent what is actually going on. Additionally, if we have a shape that is not a sphere, then the charges don't equally distribute themselves. And this is just going to be kind of a basic introduction because actually we require more advanced concepts to get a little more in depth into this. But if it's not a perfect sphere, then the charges tend to build up at the points that are furthest kind of away from the center. So we can see that on this egg-shaped one, they're here. And the reason is if you think of force, we haven't learned all about the forces yet. We'll get to the numerical calculations here in a sec. If I were to look at a point in the center, basically the charges are all going to move themselves around until they're in equilibrium, which is going to mean that all of the electric forces would have to cancel themselves out. And in terms of electric field, which is our lesson for tomorrow, or the next section, the electric field inside the conductors is zero. In order to have an electric field inside being zero, you have to have no net force. So if I picture it, if I have a positive charge here, it's only that distance from the center if I have a charge here at the center, whereas these ones are further away. Well, if we think about it, you kind of relate it back to gravity. If you have a charge that's further away, it's probably going to be exerting an a smaller force on the center. So if I want it to have that point to have the same force on the center as this point, I'm going to need more charges. So just in general, you're going to get this buildup of charges kind of at the edges and at the points of the objects. Now, this is going to relate to our electrostatic discharge. So when we talk about electrostatic discharge, we're talking about lightning, we're talking about like the plasma balls, Tesla coils and things like that, where you can see kind of this visible static discharge. I had some weird fiber blanket that when it was super dry and cold in winter, at night sometimes you could hear it crackle when I moved it. Kind of if you've had like a wool sweater taking out of the dryer, you might hear those crackles. Well, if you actually turn the lights off, those crackles are static discharges, and you can see little purple lightning flashes along that blanket as those charges discharged. And so that's kind of actually how lightning happens is if you have like a big cloud, and my background is actually atmospheric science, so this is always fun for me. Basically, you have like falling snow particles and wind particles that are pushing other particles up. So as those particles collide, they actually cause a transfer of charge, kind of like by charging by friction. And so what happens is you end up with like negative charges kind of built up aloft and positive charges kind of built off down below. So you can see that if those charges get strong enough, then you're going to get a static discharge and you're going to get lightning in the clouds. Well, what's going on at the ground? If you picture the ground here, well, your ground, let's say I've got a tree here. Your ground starts off as neutral, but I've got those positive charges built up. So kind of like when we talked about polarization and things like that, that is going to cause some of my electrons from the ground to kind of build up in the trees. Or in your hair, if your hair stands on end behind a storm, they're going to try and get to the extremes. And then if you get a strong enough buildup, that's when you can get lightning between the positives and negatives there. And also your ground becomes positive when those negatives move up. And so then kind of outside the storm, you actually end up, those positives kind of get repelled here. Actually, the electrons are getting attracted in, so the positives are being left on the outside. You can also get the worst lightning is actually outside of the storm, the strongest lightning bolts, because they go from the very top of the storm down to the very bottom. So some of the most dangerous lightning is actually that clear sky lightning where you can see the storm in the distance. because it's actually going through the largest distance, you'll have the largest buildup of charge and the largest lightning. Kind of fun with that. So, so that's kind of what's happening. So when you have these unequal distributions of charge, these areas with a high density are where that discharge is going to happen. With your plasma ball, it just kind of does its own thing kind of everywhere because it's a sphere. Until you put your finger in place, and then you're kind of affecting the electric field with the charges that are built up in your fingers, because the charge and attraction that's going to occur between your finger charges and whatnot. So if we look here at John Travoltage, so he's got some rubber shoes and he's walking on, say, a wool carpet. So when we look at the triboelectric series, as he moves around, his rubber is going to be more electronegative, so the electrons are going to get attracted. At the same time, the carpet's becoming positively charged. So those electrons are going to kind of build up. They're going to kind of move. They're going to repel a little bit. It's not a perfect simulation, but you can see that they're kind of spreading out, but they're kind of building up on his extremity here. However, if he brings his finger close to that door handle, that connection there to ground can actually cause the spark, the arc, and actually cause those electrons to jump from his finger to the door. And that happens like when you go to reach for a door handle. I get shocked by my car all the time, or my dog, and whatever. And so that's that electric discharge. All right, so now let's get to the calculations. So the law that describes kind of the magnitude and direction of these forces is Coulomb's law. Now, this is an equation that is on your formula sheet, but it's not technically a fundamental equation in terms of electromagnetism, because it's not one of Maxwell's equations. As I mentioned earlier, there are 4 equations that define all of the relationships between electric and magnetic fields, and this isn't one of them. Although it can be derived from Gauss's law, which is one of Maxwell's equations, and that's our topic for a couple lessons from now. So although we will use Coulomb's law, it may come up a couple times in the course. It's not kind of one of these groundbreaking discoveries that we think of that has defined our physics understanding throughout the years, or the decades even. But what it says is basically if you have two point charges, there's going to be a force of attraction or repulsion between them. It always acts directly along the line between them when they're separated at some distance r. There is a vector calculus definition of this equation in which r is a vector, but we're not going to use that version of the equation. But technically r would point from one of them to the other. Then you would have positive and negative forces as a result. Now, if you look at this equation, it looks a little similar to our universal gravitation, or our gravitational force is g m1 m2 over r squared. So it has the same kind of structure. And we're going to take a look at the relationship between these two equations in a little bit. In this case, we're using F12, and that's between charges 1 and 2. Sometimes we'll do 3 charge or 4 charge systems, in which case keeping track of which charges are which are important. So you will see I use a lot of subscripts, maybe an excessive amount for what you're used to, but just to try and make sure I'm plugging the right values into the correct locations. So R12 in this case is the distance between the 2 charges. Q1 and Q2 are charges. Notice the absolute values right here. Those absolute values basically tell you don't include the signs positive or negative, because we're going to use like vector diagrams, force diagrams to show the direction. So we don't plug that into our actual equations. We're just going to use the magnitudes of those charges. And then this lowercase k, and that is a lowercase k, not to be confused with the spring constant, is what we call Coulomb's constant. So Coulomb's law, Coulomb's constant. And it's essentially the constant that makes this equation valid, makes it an equation rather than just a relationship. In our formula sheet, I believe we use the value of 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. Instead of 9 times 10 to the 9th, just a couple extra significant digits. But using 99 is kind of fun with that. You'll also see it represented as 1 over 4 pi e naught. K is not actually a fundamental constant. This e naught is actually the fundamental constant. It's fundamental because it's directly related to the speed of light, which is a universal, in a vacuum, which is a universal constant. So you'll sometimes see these interchange. We use K most often when we're doing Coulomb's law, and we'll tend to use the 1 over 4 pi e naught when we use Gauss's law later in the unit, because of just the way that the derivations work with Gauss's law. That's going to come up. But this E naught is 8.85 times 10 to the negative 12th c squared over Newton meter squared. That is what we call the electric permittivity of free space. And when I say free space, I mean a vacuum. And permittivity is basically like how much it penetrates. So basically it's saying how much is the electric field affected by the materials that it goes through. So that is kind of a universal constant. Air is close enough to free space that this value applies basically in all of our situations that we're working with. So those are used interchangeably, and they're both on your formula sheet. So anytime you are working problems for exams or whatever, any formula that's on the formula sheet is a starting equation. Sometimes if you are working problems from like Khan Academy, they might use different equations. You might work a problem over and over again and find this equation over and over again, and you memorize it because you've done it so often. If it is not on the formula sheet, or it's not something that we derive using equations on the formula sheet, you cannot start with it. You cannot start with memorized equations in this class, because the whole point is you have to prove your steps. This is one of the ones that you are allowed to start with. Technically, Coulomb's law is only valid for point charges that have no volume and are perfect spheres. So we can't have something that has no volume, and there's really no such thing as a perfect sphere. So really all of our calculations with Coulomb's law are approximations. And that's actually what most of physics is approximations of phenomena. We're coming up with kind of simplified versions of reality to help us explain what we see. So that is just a very simplified version. If we have objects that are not reasonably considered to be point charges, I think these are supposed to be like rods. So if I have like a rod of charge, like you cannot use Coulomb's law for this, because that rod is very, very not spherical, very, very not point-like. And there are other ways to kind of solve those problems. We won't see problems like this with forces, but we will see problems like that with electric fields, and I will teach you how to solve those problems. So with Coulomb's law, of course, you're going to have attractive and repulsive forces, and those forces are going to be equal and opposite in magnitude. So it doesn't matter. I mean, Q1 could be 10 times Q2, but they're going to be equal and opposite. And that's because when you calculate it, both charges are in the formula. So it doesn't matter which one is bigger than the other. Also, Newton's third law tells us the force of charge 1 on charge 2 is equal and opposite to the force of charge 1 on charge 2. So their magnitudes have to be the same. So don't get tricked. Okay, I do apologize for this slide really quickly. It's got animations I forgot to remove. Oh, there it goes. So, as I mentioned, this equation for Coulomb's law is very similar to the one for gravitational force. They're both based on inverse square laws. Remember, an inverse square law says that if you take a force and you take distance, it disappears really quickly the further away you get, and technically there is an asymptote here at 0, so as r goes to infinity, the force goes to 0, but never technically reaches 0. You have the product of masses versus the product of charges. The big difference is that gravitation is attractive only, and the electric force can be attractive or repulsive. But if you think about it, if I have a charged particle here, and I have a charged particle here, and the ground is here, and I asked you to find the net force on one of these particles, well, they're going to have some sort of electric force that is attracting them together, but technically the Earth is pulling them to the ground because they do have mass. That is going to complicate problems if we always have to deal with the gravitational force and the electric force. So is there a way that we don't have to complicate other problems? Is it valid to just ignore the gravitational force and just look at the charges and the forces between the charges in terms of that? Also, there's also technically a gravitational force between them because they have masses. So do I have to look at that? Well, we can do a nice little calculation to kind of prove how we can deal with this conundrum. So what we have is we have a hydrogen atom. A hydrogen atom is made out of one proton and one electron. So we're using lowercase m for the electron. On your formula sheet are the masses of electrons and protons. Remember that the mass of a neutron is essentially the same as the mass of a proton, as long as you go out to a few different, if you get far enough in the sig figs, a neutron technically has a tiny bit more mass, but they're effectively the same to about 3 sig figs. On the formula sheet, we've got a couple extra sig figs for the masses. But the mass of that electron is about 9.1 times 10 to the negative 31 kilograms, and the mass of the proton is 1.7 times 10 to the negative 27 kilograms. So the mass of the proton is about 100 times that of the mass of the electron, which is why if you had protons and electrons moving towards each other, the electron would have a larger acceleration because it has a much larger mass. Additionally, the charge on these, it's kind of hard to see there, that's a positive E and a negative E. Remember that E is that 1.6 times 10 to the negative 19 coulombs for that elementary charge. So if we were to use those equations and calculate the gravitational force and the electric force, we are going to use R to be 5.3 times 10 to the negative 11th meters. Now the reason we're going to use that R is if you picture the atom, that electron is not moving in circles like Bohr originally thought, right? It's actually moving randomly. It's coming in, it's coming out, it's moving this way, moving in straight lines all over the place. If you were to take 1,000,000 snapshots of a hydrogen atom and calculate the radius from the proton to the electron for each of those 1,000,000 snapshots, this 5.3 times 10 to the negative 11th meters is the average position of the electron. It's what we would in kind of like old school chemistry define as the position of the first orbital, the first shell in the hydrogen atom. It's also going to be half the atomic radius. If you look at the atomic radius, the atomic size of a hydrogen atom, this is half that because it's half the diameter. So that's where that value comes from. So very representative of the atom. So if we calculate that gravitational force, plug in all our values, you should get a gravitational force of 3.6 times 10 to the negative 47 newtons. That is very, 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 very small. Very, very, very small. But we know that our charges are also very small, right? 10 to the negative 19 coulombs. But if you plug in the electric force, they're using this 1/4 pi E naught, which is the K, coulombs constant. We get 3.6 times 10 to the negative 8th newtons. That is huge compared to this itty bitty 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 teeny gravitational force. So what that tells us is, because this is so big, and you can do some statistical analysis to prove how big it is, that we can neglect the gravitational force between those particles and also between the particles in the Earth if you do those calculations. My favorite word is negligible. Negligible means so small it can be ignored. So from now on, unless we're doing something macroscopic where we're not dealing with charged particles but charged objects, like actually in the next example, we are going to be able to just look at the electric force using Coulomb's law for these particles. So here's this example where you can't neglect it. So we're actually going to take physical spheres with mass m and charge q. We're going to hang them from strings. You could do this with balloons. Charge up 2 balloons, and they'll repel each other, hang them from strings. And you could actually do this experiment. And if you all had balances and rulers and stuff like that at home, this would actually be a fun one to do. But I'm going to assume that all you have is a calculator, so our lab is going to do this with a simulation. But in this case, our goal is to find the charge Q as a function of theta and L. We could also have solved for the angle theta. We could have solved for the separation distance between them. I don't know how much experience you have with non-numeric problems, or what they might be called algebraic solutions. But when we're doing electricity and magnetism, it really sucks to plug in numbers. Because if you looked at the numbers on the previous page, you've got all this scientific notation, times 10 to the negative 47th. Like, the likelihood of you making a mistake while doing a calculation is high. So we will do calculation problems. If we do calculation problems, there's not as many points usually for a correct answer as it is for the steps to get there. But a lot of our problems will involve variables only, and not actually plugging in values for those variables, just to kind of save time. We can also learn really cool things about some of our scenarios by sticking to the variables. So if I want to solve this problem, I need to go back old school mechanics. So I'm going to draw a free body diagram. These are identical spheres, so I only need to look at one of them. I'm going to look at this one on the left. So there's going to be a gravitational force pulling this sphere down, and there's going to be a tension pulling up and to the right, and they're going to have the same charge, so they're going to repel. So I'm going to have that electric force to the left. So if I'm going to find the charge Q as a function of theta and L, I need to get an equation that doesn't have gravity, doesn't have electric force, doesn't have tension. So I'm going to need to start writing this out. But this is a two-dimensional problem, so I'm going to have to go ahead and set up some coordinate axes. And I notice that my tension is at an angle. If I look, this angle theta right here with my trig is going to be the same as that angle theta right there. There's some sort of like parallel lines with a bisector. I don't know the names of all of them, but with our geometry, you could prove that those angles are the same. So what I'm going to do is I'm going to take my tension and resolve it using that as my angle theta right there. So I'm going to have an FTX and I'm going to have an FTY. You may have worked problems where your teacher used just a capital T for tension. I occasionally did that, but capital T also stands for period. It stands for Teslas in electricity and magnetism. So I usually use all of my forces with a capital F and then a subscript telling me what it is. It doesn't really matter what variables you use in your diagrams. If you just want to write out tension, you can. Just be careful that when you're working a non-numeric problem, that at the end, your variables have to match whatever it is that it says in the problem, plus universal constants like lowercase g or lowercase k now for some of those constants. So I'm going to write net force equations. So I have a net force equation in the x direction, and that is going to be FTX minus my electric force. And this is going to be an equilibrium, so that's going to add up to 0. And then I have in the y direction, I have FTY minus FG, and that adds up to 0 as well. So I'm going to go through and start subbing in. With my trig, my FTX is the opposite side of that triangle, so it's going to be based on sine. So I'm going to have FT sine theta. And if I add the F electric to the other side, I'm going to get that as equal to F electric, which is going to be my K Q1 Q2 over R squared. please, 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 I know every teacher is different, but it's actually really important that when you're writing your net force equations in equilibrium that you show that you're setting equal to 0, because that is a big assumption. So please do not start equations by just setting tension equal to electric force. Please show the actual net force equation and show that it adds up to 0. I know it might be a little nitpicky, but it is better physics. So then I do the same over here for my Fy. And so I'm going to get Fty, which is going to be based on cosine. So Ft cosine theta. And that's just going to equal mg. I don't need to use universal gravitation because I'm in Earth's gravitational field is what I'm assuming. So I'm on my way to getting everything in terms of just Q, theta, and L in constants. This tension is going to be a big problem. So what I'm going to do is solve this one here for tension. So tension is going to be mg over cosine theta. And I'm going to come in and sub that over here. So I'm going to get mg over cosine theta times sine theta, don't forget that guy, is equal to k. Now both of these had the same q, so q1 and q2 are both q, so that's just going to be q squared over r squared. So this looks pretty good, and I'm looking at my variables. K is Coulomb's constant, that's allowed. G's the gravitational acceleration, that's allowed. I have m. M's not in there, but I think it's supposed to be in there. I feel like that's going to need to be in my list. So I think this might have to have M. But R is not in my list. And I feel like I can find R. So let's take a look. So if I look at R, R is actually going to be this whole distance right here. That is R. I also have a triangle here. Where L is the hypotenuse. I don't have L in this at all, and I definitely need L. Like I said, I feel like we forgot M in the list when we went through creating that variable list. And then I have a theta right here. So if I look at this triangle, R over 2 is going to be that opposite side of the triangle where L is the hypotenuse. So I could write an equation for sine theta, and I can say that sine theta is going to be R over 2 divided by L. And then if I solve for R, R is going to equal 2L sine theta. So I'm going to save that for later, because right now it's squared, and I know because I've done this before that I can actually simplify this down a little bit so I don't have to get crazy with square roots and stuff. But I'm going to leave that right there. So I am looking for Q. So I do need to get Q by itself. I do notice here that I've got a sine on top and a cosine on the bottom. So I'm going to make that a tan. So I get mg tan theta is equal to k q squared over r squared. So solving for q, I'm going to multiply the r squared and divide by k on both sides. So I get r squared mg tan theta over k is equal to q squared. I can then take the square root. Notice that I can actually get a plus or minus. I don't know whether these charges are positive or negative, but they both have to be one or the other. So q is going to be the square root of r squared, so I can pull that out in front. So that's going to be r times the square root of mg tan theta over k. And then I can take this guy and plug it in for r. So I get that q is equal to 2L sine theta times the square root of mg tan theta over k. So like I said, I don't think there's any way to eliminate m So I think that was a mistake. I think M was supposed to be in our variable list at the top, and I apologize for that. I will fix that for next year. So we have that problem. So this is a very iconic problem. If you were to look online and Google charge problems, like this will come up. The other really, really common problem are multiple charges. So in this example, we have a positive charge Q1 located on the y-axis. We have a second charge located on the origin, and another one located on the x-axis. They didn't give us a picture right off. I will tell you, they've got one here for us. On your tests, I will always give you a picture because I don't want you to like misread one tiny thing in the problem and your picture's wrong from the start. So we're always going to have that in here. So we're going to add that information in. So here is our setup with our setup information. And our goal is to calculate the net electrostatic force, which is that electric force, Coulomb's law, on Q1 due to the other two charges. So I'm interested in what's going on with this charge right here. So I have to look at the other two charges. So if I look at Q2, they're both positive, so that's going to create a repulsion force. So Q2 is going to push Q1 away. So I'm going to call that F of 2 on 1. Now the reason I'm doing that is because I have 3 charges and I'm going to have a lot of subscripts, and I want to make sure that I'm not going to make a mistake with my charges. And then if I look at Q3, that is a negative charge, so it's actually going to pull in and attract Q1. So I'm going to call that F of 3 on 1. So once again, I have a two-dimensional problem. A simpler version of this is a problem where they're collinear. Collinear means they're all in a line. So you'll sometimes see them like this, where they're all in a line. So that way you don't have to worry about the two-dimensional problems. I think there is an example of that in one of the tutorial videos I shared. But here we go. So we got 2 dimensions. So once again, we have to draw on our coordinate axes. So I can see that F3 on 1 is at an angle, so I'm going to need to create a triangle. I'm going to use a similar triangle to the one that's drawn. So I'm going to have F3 on 1x, and I'm going to have an F3 on 1y. Fortunately, F2 on 1 is only in 1 dimension, so that'll simplify our math down a little bit. So I'm going to write a net force equation for Q1 in the x direction, and that is going to just equal F3 on 1 in the x, because F2 on 1 doesn't have a component there. And then on our y direction, FQ on y is going to be F2 on 1 minus F3 on 1 y. So I'm going to start over here with the x component because it's a little simpler. So I'm going to sub in, so FQ on 1x. Please always work in equations. Do not leave expressions hanging around. It can be very difficult to follow work. And make sure your work is logical. For example, I am working here on a very small area, just like you might be working on a test, and I'm going to always try and provide a flow if I'm having to move things from one location to another. Create a roadmap for your reader so that they understand what you are doing and why. So once again, I use these subscripts to keep my charges the same. So I'm going to do K, and then that's Q3, Q1 over R31 squared. And the X component is the opposite side here. So I'm going to tack on a sine theta. So subbing in, because once again, this is non-numeric. Q3 is negative 2Q, but once again, I really just use the absolute values. So that's going to be 2Q, and then Q1 is a positive Q, so that's just going to be Q. R31 is going to be the distance between R3 and R1, which they define as 2D, but that is squared. And then I need to find sine theta, and there's a lot of different ways to do your trig, but what I'm going to do is I'm going to do a Pythagorean theorem with this triangle right here made by D, 2D. I'm going to call that X for right now. So I'm going to have that x squared plus d squared is equal to 2d squared. So that's going to give me that x is equal to 4d squared, x squared, sorry, 4d squared minus d squared. So x squared is going to be 3d squared, which is going to be the square root of 3. So x, sorry, trying to do that there. So that tells me that x is the square root of 3 times d, if I were to square both sides. So sine theta then is going to be x over 2d. So that is going to be the square root of 3 times d over 2d. So simplifying, one of these d's will cancel. I'll have a 2 cancel here. So this gives me the net force of Q1 x is equal to kq squared. I'm going to tack in that square root of 3 from on top right there, and that's going to be over 4d squared. So then I come over here to the y component, and my q1y is going to be f2 on 1. So that is going to be kq2 q1 over r21 squared minus f31y. So if I wanted to look at f31, that's going to be this part right here. So I'm going to just skip a little bit, and that's going to give me k times, well, I'm not going to skip that much, 2q times q over 2d squared. And that's going to be based on cosine theta. So I'm not really skipping much. I do need to find cosine theta and simplify. So I'm going to get fq1y is going to be k. q2 is just q. q1 is q. r21 is just d, so that's going to be d squared minus, that's going to give me 2kq squared over 4d squared. And cosine theta is going to be, so like I said, I'm having a little, trying to cram the stuff in. Cosine theta is going to be adjacent, which is going to be d, over hypotenuse, which is 2d. So that's going to be d over 2d. So this d cancels that d, that 2 cancels this 2. So I get my net force of q1y is going to be kq squared over d squared minus kq squared over 4d squared. So that's like 1/4. So this gives me the net force of q1y is going to be 3/4. It's going to be kq squared over d squared. Now, the problem here is that I have only found components. I have found my, sorry, there you go, my x component and my y component. If I wanted to find the net electrostatic force, I would need a magnitude and direction, or I'm going to shortcut it because it doesn't want magnitude and direction, and I'm going to use unit vectors. So with unit vectors, you have your x direction, your y direction, and your z direction. X is I hat, y is j hat, z is k hat. And you can have your positive and negative. If you are unfamiliar with unit vectors, I strongly suggest you find some tutorial videos specifically on unit vectors. I'll try and add one in if I remember to my stuff. But it's something I normally teach in University Physics 1, but I know not every teacher does. But it's really handy because if I wanted to then write the net force of Q1, I can just do the square root of 3kq squared over 4d squared. and that is in the positive I hat direction, because that was in the positive x direction here. And then I can add 3 over 4 k q squared over d squared. And that is in the positive j hat direction, because it came out as positive, so f2 on 1 is bigger than f3 on 1y, so that's in the positive direction. And that can be my answer. Now, if it did ask for magnitude and direction, what I would have to do is I would have to use the Pythagorean theorem to find the hypotenuse of that. I'd have to find the angle, and that would be really messy. I don't need to do that unless it specifically asks me for it, but that's probably what you are more familiar with. Additionally, we're not working with things like north and south and east and west, or above or below the horizon, so direction gets complicated. What I would end up getting, if I was to actually work this out, is my net force on Q1y is up. My net force on Q1x is to the right. So if I was to go through and kind of combine those together, wherever that ends up, that would be my net force of Q1. And then I would need some sort of angle, like phi. I've already used theta, so I'm going to use phi for that. And then like phi might be some angle, what would that be? That would be clockwise from the positive y-axis. So I would have to find the magnitude of that vector using the Pythagorean theorem. I would have to use tangent theta or arctangent to find that angle phi and provide some reference direction for which way it went. That'd be obnoxious. Unit vectors, amazing. So if you don't know unit vectors, try and learn those. There are additional tutorial videos that I've picked to kind of focus on some of the types of problems you might see. You'll see more problems in your Mastering Physics assignments. If you need any help, please reach out first in the discussion forum if you can. Remember, you have to have 100-word minimum for your posts. Try to provide an explanation of where you're at, not just, oh my gosh, this is the hardest problem in the world. Just say, hey, I've tried this. I've looked at this problem in the textbook, or I found a similar problem in our notes, but I don't understand how we got from part B to part A, or I'm stuck. This is what do I do next? Please ask for help. Come to office hours if you need additional help, tutorials, anything you need, but get help as soon as you need it. Thank you. Have a great day.